welcome to the introduction of the Nvidia Modulus library. What is Modulus? Modulus is a neural network framework that blends the power of physics and partial differential equations with AI. A friend once said, "Neural networks are the solution to all the world's problems." He was joking, but statistics can be used to solve differential equations in a very clever way. How come? I assume you know that if we cannot arrive at the solution of a differential equation analytically, we must accomplish an approximation that is as good as possible. It's an optimization problem, therefore. And AI is really good at optimization. Indeed, a neural network can approximate the solution to a differential equation and boundary conditions. And notice that I haven't defined what a neural network is, and in fact I won't. The beauty of the approach is that you only need to know what you are optimizing, not how you're optimizing it. You are free to research how neural networks work, but the idea is that the neural network is trained with respect to a loss function derived from the differential equation and boundary conditions. That is to say, you only need to know how to formulate the problem, and to formulate the problem is to formulate the loss function. Therefore, to minimize the loss function is to solve the differential equation. That is the beauty of this approach. Let's do an example very quickly. Suppose we have the following differential equation and boundary conditions. Very straightforward example. Focus at boundary conditions right now, below. We know that the unknown function u must be 0 at the boundaries x equals to 1 and x equals to 0. So let's call the approximation unet. We don't know u, and we won't ever know u. We are going to only get a good approximation called unet. And this is how we encode the boundary conditions as a loss function. The intuition is very simple. If we are too far from 0 at the boundaries, that means the model is wrong. That's a loss. That's why we call it a loss function. We define the boundary conditions to be 0, therefore, if we're away from 0, that's bad, that's a loss. Whether that's at any of the boundaries, as you can see here. A loss function ought not to be unique in most cases, but a sum of squares, in this case, is a good start. It takes into account the magnitude of negative values, because we're squaring them, and encodes the information at the boundaries very well. But we could have taken the absolute value as opposed to squaring the errors, but you gotta be clever about how you define your loss function. The better you define it, the better your approximation is going to be. But this is good enough in this case. Now, that was for the boundary conditions. What about the actual differential equation itself? We want our loss function to take this into account. We can represent how bad the model is by squaring the magnitude of its error. That's it. It's pretty much the same idea. Let's go back very quickly. We have the second rate of change of u with respect to x here. So assume we move the expression f of x here to this side, and then you have one thing minus the other equal to 0. And if that's not true, that's an error. Therefore, we capture that as a measure of the error. We square that for the same idea as before, and we take the average. We sum all the errors up, and we take the average. That's about it. Then we have the loss function that captures the error at the boundary conditions, at the boundaries, and the loss function that captures the actual error of the overall model. We sum that up, and that's our loss function. And that is the problem, right? Formulated. We minimize the loss function, and therefore we solve the differential equation. The differential equation with this approach. So that's the idea, really. Here are the references where I learned all of this. You should check them out. I in particular recommend the old user guide. Take a look at it because I liked that format. But the new one also is really nice. It's actually more traditional, it's like an actual documentation